Hello and welcome. I am Caitlin Sachs, a senior producer for Nova, and today we are going to be having a conversation with David Kaiser, and we're going to be talking about the fundamentals of physics. And by that, I mean the Fundamental Physics group. And that's physics with an F, Fysiks. We'll explain that in a bit. But these were a group of physicists who held quite a reputation as the hippies of physics, but who also helped catalyze the advancement of quantum physics. So we're going to get into that. We're going to delve deep into some trippy stuff like the nature of quantum entanglement and how these aspects of nature are being used in technology today. So David Kaiser is a professor of the history of science and a professor of physics at MIT. He's the author of several award-winning books on the history of modern physics, including How the Hippies Saved Physics, Science, Counterculture, and the Quantum Revival, the subject of which we will be talking about today, of course. He's also featured in a number of Nova documentaries, including Particles Unknown about neutrinos, Einstein's quantum riddle, what is the universe made of, and most recently this year's Decoding the Cosmos. I have to say, when I started to look up how many films David has been in, I just stopped there. I figured that's enough. But every time we at Nova talk to David, our mind is blown. That's why we've put him in so many of our films, some of which he has actually helped inspire. So my goal for this conversation today is to share that with you, to try to blow your mind without the use of any psychedelic drugs or whatnot. So, David, thanks for joining us today. Are you up for this challenge? Are you ready to blow some minds?
Well, I'll do my best. And Caitlin, thanks so much for inviting me on. It's always a treat to be able to talk with you and all the colleagues at Nova. So thank you.
Thank you. So first, a little housekeeping. This is a live conversation. So to the audience watching live, if you have questions for David, please just drop them in the chat and we will try to get to them. All right. So David, first let's start with the basics. What was this fundamental physics group?
Yeah, well, as you say, they spelled physics with an F. That already gives you an indication they were open to having a pretty fun time. They didn't take themselves too seriously, and that's part of what drew me to them actually when I was working on this project. So the Fundamental Physics group was an informal group. They weren't formally organized in any way. It was a ragtag group actually of not quite a dozen people, and they all kind of found each other in the San Francisco Bay Area in the early and mid 1970s. They began having regular meetings, most of the time every Friday afternoon, for some big open-ended discussions about basically how does the world work? What's the world made of? Things like how do they best try to make sense of things like quantum theory, which is then as now can keep us up scratching our heads at night. So they were a group of people, almost all of them had either completed PhDs in physics or were in the process. They were active grad students at the time, but they were finding a kind of frustration with the typical way that young physicists were being trained, especially in the United States at that time. They had all entered the field with these, dreaming big thoughts about quantum theory, about relativity, about black holes, about the Big Bang, about these really deep, kind of juicy mysteries of how the world works. And they each found in their kind of formal training, especially at the PhD level, that it seemed to them at least kind of narrow. It seemed to kind of cut out some of these bigger what if or how does it all work kinds of questions that had helped inspire them, when they were young kids, teenagers and so on their own. Combined with that, they had the remarkable bad fortune of trying to enter physics at what turned out to be one of the worst times to try to get a job as a young physicist. It's through no fault of their own. The entire field, especially in the United States, although it turns out similar trends in many parts of the world at that time, there was a kind of rapid cut in the demand for young physicists, not just in university positions to become young professors, but also in industrial labs, in government labs. There was just a huge fall in the demand, and the supply was exploding. So it was a really tough time to make a kind of typical career in physics. And these folks decided, well, they weren't finding their main questions answered in their kind of typical curricula. Some of them felt like, what do they have to lose? Because the typical career path was shifting kind of under their feet. And so they kind of bumbled along and found each other through the kind of accidents of history. And they made a little kind of study group, a discussion group in Berkeley, California. And one of the topics they were most excited about was quantum entanglement, and then topics that would spring out from there.
So I want to get to quantum entanglement because that requires a pause to try to wrap our
Right.
heads around it. And I will say, despite having made a film on it, I still haven't wrapped my head around it. I don't know if anybody has actually fully wrapped their head around quantum entanglement.
Right.
But first, you also explain in your book, in the 1970s-ish, there's a growing New Age movement pulling in some aspects of Eastern mysticism, and they're also seeing something really appealing or some alignment with the principles of quantum physics. Can you explain a little bit, like what was it that they were seeing in quantum physics?
Yeah, I should start by saying it's a great question, Caitlin. So, the group is about, again, maybe 8 to 12 kind of core members, and they would kind of accordion week by week, more people would come and go, but there was a core group. And even among that group, there was a wide range of opinions. Their own opinions or ideas would change over time. So, so even though it's not a huge group, there was variety among them. And for some of them, just as you say, they got very, very interested, really enthusiastic about all kinds of spiritual and intellectual traditions beyond the ones that they'd experienced through their kind of typical training. And for some of them, ideas from various strains of Eastern kind of spiritual or mystical traditions really, really excited them, like Confucianism, like Taoism or Buddhism, Confucianism. They're not the same as each other, those traditions. And some of these folks got excited about trying to do a kind of compare and contrast. So some of them really became they would read a lot of books. They'd go to lectures in the Bay Area at a time when interest in these topics was growing, especially in the San Francisco area at that time. So one of the things that got some of these folks excited, like Fritjof Capra, who was a member of this group, he was originally actually from Austria, but was at that point doing a postdoctoral fellowship in California, in Santa Cruz, not so far from Berkeley. And so Fritjof was really noticing in his explorations, there were ideas, at least in some of these Eastern traditions, of a kind of underlying wholeness, a kind of hidden connectedness among things that might appear to be separated. That was one thing that really resonated with Fritjof as a young person, because it seemed to be parallel, at least, with ideas that he really was grappling with day by day in areas of quantum theory, that in quantum entanglement, but not only in that. Is there a kind of could the whole be more than the sum of its parts, we might say? And that was something that he was exploring or getting exposed to in his reading, in his lectures, and in his own increasing kind of meditations and so on. That's an example. He went on to write a best-selling book about that called The Tao of Physics, that, as far as I know, is still in print. It's become a blockbuster international seller. But it was really a kind of pet project, a passion project of Capra's, because he was trying to really sit with these two different sets of ideas that to him seemed maybe to have things to offer to each other. So that's a quick example that a kind of notion of subject and object might not be the same as a kind of typical or traditional Western view. Is there a role for the observer that might have an impact on what even gets counted as being observed, or what we attribute to being something as a part of objective reality? Are we bringing something to that? Controversial questions to this day in the topic of quantum physics. But again, in the 70s was getting some of these folks really interested about possible connections, or at least parallels, with things they were just beginning to explore.
So it sounds like the idea of quantum entanglement, which I want to get into in just a moment, but
Yeah.
basically the idea is that things can communicate faster than the speed of light. And also this idea of the role of the observer in a system are things that both the physicists and I don't know what you'd call them, philosophers of the day were very interested in. So let's get into what those are exactly from a physics perspective. So
Yeah.
quantum entanglement. Start us at the beginning. This came about what, in the early 1900s?
Well, yeah, it really gets articulated in the 1930s, mid 1930s, so long before the hippie days that we've been talking about. And in fact, entanglement is in that era was most closely associated with names that really we do know, that we think of as kind of unhippie-ish, like Albert Einstein and Erwin Schrödinger. They each had kind of bohemian streaks in their own day, but they certainly weren't 1970s California hippies. Let's be clear about that. And so what they were doing
They weren't the OG hippies.
right. That's fair to say. I think they'd agree with that statement too, if we could ask. But what they were doing, these were some of the most important architects of quantum theory. They each won Nobel Prizes for their work contributing to quantum physics. Also, it's important to remember is that both Einstein and even Erwin Schrödinger, by this point, became pretty convinced skeptics or critics of quantum theory. So they helped build this amazing edifice And then over the intervening decade, from the 1920s to the 1930s and indeed beyond, Einstein and Schrodinger each started kind of nursing these really significant questions and even kind of doubts, criticisms. And so each of them began thinking about what we now call quantum entanglement, partly because they were convinced this couldn't be real in the world. They were trying to suss out, does quantum mechanics predict such strange sounding things? And if so, isn't that a problem for quantum theory, right? So they're helping to articulate things. We still read their papers with great profit to this day, exceptionally clear from the 1930s. But their goal was not to say, hey, there's this cool feature of quantum theory, isn't that great? Their goal for each of them, Einstein and Schrodinger both, and they're kind of egging each other on through letters at the time, was to say, this sounds just too strange to be real. It sounds like spooky ghost stories as opposed to real physics. Nonetheless, what they began to identify is that if one took the equations of quantum theory really at face value, as they'd been worked out already in the 1920s and 30s, quantum theory seemed to suggest that under certain circumstances, if there were two little bits of matter, two particles, two things we could imagine performing measurements on or interacting with in a laboratory, if they moved very far apart, arbitrarily far apart, that they would still retain a kind of connectedness. So they weren't clear at the time, did it involve actually communication, a word that you'd used? There's some kind of connection. In fact, as Einstein famously called it dismissively in a letter to a friend, it looked like a spooky action at a distance. For him, that was not terms of praise. It was like ghost stories of weirdness. So the idea was the equation suggested that there was a kind of, again, that a quantum system had more to it than just adding up everything you might know about one piece and adding what you might know separately about a second piece. That there were connectedness or correlations or connected behaviors that the equation suggested could be real, beyond what you would ever be able to kind of think about in a classical physics or say in a Newtonian system. And for Einstein, as for Schrodinger, this spelled trouble, not excitement. Nonetheless, they wrote these papers in the 1930s. Actually, it was Schrodinger himself who coined the term entanglement in English. He had just fled his job in Berlin because of the rise of the Nazis. He was doing more and more work in the English language. Schrodinger coined the term entanglement. Einstein had likewise fled Berlin earlier and had resettled in the United States. So the two of them were now exchanging letters across the Atlantic Ocean and really kind of, as I say, kind of coaxing each other to articulate their criticisms of quantum theory around topics like entanglement. So that's where this topic kind of stayed. So a number of the earliest kind of proponents for quantum theory, like Niels Bohr and his younger colleagues, Werner Heisenberg, Wolfgang Pauli, a lot of these folks, were kind of not too impressed with Einstein's critique. Some of them wrote their own responses that, frankly, are hard to follow today, and some people call the responses kind of muddled. It was kind of, a debate that seemed not to go anywhere. And so Einstein and Bohr remained lifelong friends, but they never convinced the other of how to think about quantum theory, about topics like entanglement in particular. And basically, they both died, having not convinced the other after discussions that had unfolded over decades, nearly 30 years. Soon after each of them actually had passed away, as it turns out, a much younger physicist and member of the next generation named John Bell, who's originally from Northern Ireland, was kind of dissatisfied by the state of play, by the state of discussion of these topics. And so he read Einstein's paper very, very carefully, the so-called EPR paper. Einstein had written this paper with two younger colleagues, Boris Podolsky and Nathan Rosen, so we usually use their initials, EPR.
This is the paper saying that quantum entanglement proves quantum theory. There is a problem with quantum theory.
That's exactly right. So that's right. So the EPR paper published in spring of 1935, that's Einstein, Podolsky, Rosen, identifies this strange prediction in quantum theory and says that's like too bad for quantum theory, right? And so John Bell, much later, was reading that paper with great interest. He read and was really dissatisfied with Niels Bohr's response that had also been published in the 1930s. And so Bell returned to this with, let's say, fresh eyes, a younger generation, not quite beholden to the same, sort of all the same assumptions that had animated the earlier folks. And what Bell did was he realized there might be a way to really test this question and not just argue late at night through kind of cigar smoke among friends, which is how Bohr and Einstein tended to talk about it, pipe smoke or cigar smoke. And so John Bell says, maybe we could actually force a showdown. Maybe there's an empirical contrast between a world that behaves the way Einstein assumed it would have to, and a world that would obey these strange-looking equations of quantum theory. And so Bell divided what we now call, in his honor, Bell tests. He said maybe there's a way to actually subject pairs of particles that have been prepared a certain way, conduct a series of measurements on each member of the pair, and try to understand whether their behavior really lines up, is correlated in this much stronger set of correlations that quantum theory seemed to suggest. So what he did is he basically took the core ideas that Einstein and Podolsky and Rosen had put forward in the 30s and tried to codify them. What Bell did was kind of codify them. Any theory of nature that obeyed what Einstein and his colleagues considered kind of non-negotiable, the core principles, that must lead to different predictions for real experimental outcomes. Bell is the one who really first showed this, compared to the now, by that point, fairly standard predictions from the equations of quantum theory. And if one designed these clever experiments and conducted them very carefully, maybe we could suss that out. So that's what Bell did. He published that article late in the year of 1964, so almost 30 years after the EPR paper and Schrodinger's similar work from the 30s. And then this amazing body of work, which now we teach all our students, we consider one of the most significant papers in the history of modern physics, John Bell's article, it went nowhere. It was completely ignored in its early days. In fact, it was published in 1964. It received 0 citations in the worldwide scientific literature the next year. It received 1 citation 2 years later, and that was by John Bell himself. It was a self-citation. No one was picking this up, literally no one. And then what caught my eye was among the first to begin to pay attention was this group that you and I began talking about just a few minutes ago, the group that had called themselves the Fundamental Physics Group in Berkeley.
The fundamental mysteries of the universe. Why was nobody paying attention to that for a generation or more?
It's a good question, and that's partly what I tried to explore in the book that you'd mentioned. I think a lot of it has to do with the changing way in which physicists were training newer physicists, and the changing kind of landscape in which young physicists found themselves during the period between the 1930s and the 1960s, or early 1970s. A lot changed in the world, a lot changed in physics in between. One of the big ones, of course, being the Second World War. These enormous weapons projects, like the nuclear weapons project headquartered at Los Alamos, the Manhattan Project in the US, and these huge kind of applied physics projects that really enveloped a generation or two. Now, what happened, especially in the United States, and not only there, coming out of the Second World War, was a pretty significant reorientation in what seemed to count as worthwhile physics. I should clarify, most physicists in the United States were not working on weapons projects after the war. Weapons projects continued to grow. The supply of young physicists grew faster. So it's not that everyone was working on bombs afterwards at all. Those projects were going strong, but it was a minority of the population. But there was a kind of ripple effect nonetheless. And that really caught my eye when I was wearing my historian's cap. If you look at changing textbooks in quantum theory, look at changing lecture notes, look at changing homework assignments and these things, we have paper traces. This was long before the internet, so people had to write stuff down and like Xerox it, which is the best thing for historians. Paper trail all over the place. You see this transition in what sort of is taken to account as really kind of worth celebrating or worth focusing on in training young scientists, young physicists in particular. So it's not that they all started focusing narrowly on nuclear reactions or let alone weapons stuff, but there was a focus on a kind of pragmatic approach that the attitude became, it was often kind of caricatured by the saying, shut up and calculate, which was attributed to Richard Feynman. It's not clear if he ever said it, but it rang true with an attitude that he and many of his generation would try to instill in their own students. That our job is not, they argued, to stay up late at night through the cigar smoke, arguing about what it all means, but actually to say, let's put these equations to work, let's find new phenomena, let's build new things, and let's ask different kinds of questions, not bad questions. I want to be clear. In many ways, this was a golden age for physics in the United States. More Nobel Prizes than ever before. People were finding really important things that we still take for granted and teach our students today. It wasn't bad physics. It was a different set of priorities.
So is it safe to say that physicists of that day were creating technologies, advancing science that relied on these fundamentals of quantum physics to be true? They just weren't asking why they were true.
I think that's a good gloss. I think that's exactly right. That's consistent with, the questions they were asked for their homework assignments, the way the textbooks were being kind of rewritten in the years soon after the end of the Second World War. I think it's exactly that. There was another part that really intrigued me that I think at least accentuated those trends. And that's that coming out of the Second World War, physics enrollments were growing like crazy. In fact, physics was the fastest growing field of study in the American university system of all the fields around. Every field of study was growing. There was a huge influx of new students, thanks in large measure to things like the GI Bill. Lots of people who'd served in the Second World War now had the opportunity to go to college, and some of them wouldn't have had that opportunity if they hadn't served and if there hadn't been this GI Bill. Huge, rapid exponential growth in the American university system. And again, plays out with different rhythms in other parts of the world as well. Certainly very similar growth in the Soviet Union at the time. And then kind of uneven in other places. Anyway, even as every department is growing, none grew at a faster rate than physics, partly because of the drama of the wartime projects. After the end of the Second World War, these once highly top secret projects like radar and the Manhattan Project were kind of unveiled, selectively unveiled. And young physicists became, kind of heroes, or were treated at least as cultural celebrities in a way that's sometimes hard for me and my colleagues to imagine today. Some of them were treated as really just basically like movie stars. And so the enrollments were booming like never before. So that
We
means
treat you like a movie star, David.
I appreciate that.
You're a Nova movie star.
Well, yeah, the word Nova there seems to play a role there, Caitlin. Anyway, no disrespect to my friends at Nova. It's not quite the same red carpet. Anyway, I love it. But the point is, it was really a kind of cultural phenomenon in the 40s, really in the 50s, where even when like Time magazine would conduct polls of the most prestigious profession, nuclear physicists would be ranked like among the top three. We're not there these days, right? So it was really a cultural phenomenon as an educational phenomenon. And so the kind of floodgates opened. So if you ask yourself, what's it like to teach hundreds of students in a class on quantum theory when before the war it might have been dozens? As a teacher, I would imagine asking different kinds of questions. It's hard to grade 300 essays until know what it all means.
Like multiple choice.
You go to multiple choice, or you do, really good. There was a collection of really exquisite calculating skill. Again, I want to be clear, it's not like good, bad, it's shift in what gets prioritized. And that post-war generation, many of them got extremely good at calculating and doing kind of quantitative math-based problem sets. And that's not a bad thing. That's incredibly important for physics. But what got kind of shunted, what got lower priority and kind of pushed to the side, and sometimes actively denigrated, but just kind of squeezed out pedagogically as well, were these much more open-ended, kind of philosophically flavored questions about, let's try to ask qualitative questions about what it means for the world to behave that way. So I think lots of pushes and pulls on that generation coming out of the Second World War. And Bell was really educated in that era. He was one of the outliers. In fact, John Bell recalled later in his life that he was actively advised not to pursue these philosophical sounding, was it all mean questions, because it would hurt his career. And he went on to an extremely prestigious career as, let's say, a kind of straightforward particle physicist. He used the equations of quantum theory brilliantly. There are effects named in his honor in kind of mainstream nuclear and particle physics to this day. But it was really a kind of side interest that he learned to kind of keep quiet about. Even though today we now realize this was just absolutely foundational, mind-boggling work.
I really want to get to the quantum entanglement explanation, but just building off that for a second, as a historian of science, you've seen how the sort of anatomy of paradigm shifts in thinking, and is this how it always happens? Is always these outliers, or?
That's an
I'm
interesting
curious
question.
if you have any commentary on what it actually takes to make big shifts.
Well, that's really interesting. So I think I don't know that it always takes that. I think we can find examples. So this wasn't unique. Let's put it that way. This was the only time we found that kind of outlier. But I think what I find most interesting as an historian is that it's almost never the work of one lonesome, genius or outlier or anything else. But a lot of the work that my historian colleagues and I really have fun trying to do, and it involves kind of detective work, is try to understand what are the shifting institutions in which that work was being done, or in contrast to which the outlier, was positioning themselves, in contrast. So that what was the taken for granted path? And how is that reinforced? For example, through teaching, through pedagogy, through the pattern of support, financial or otherwise, for certain kinds of questions. And so the outliers, first of all, are almost never working alone. And secondly, they're in a kind of they're situated in a kind of social universe that also is not static, doesn't sit still. And that's again part of what really grabbed me about the shifts we're talking about now. The Second World War drove in the United States an unbelievable infusion of cash in the sciences and in higher education, like literally never before. And it didn't last forever. And it began to revert, the fortunes reversed equally quickly, sort of shockingly fast, with these exponential drops in things like support, roughly a quarter century later. So it's these kind of amazing play of ideas and curious personalities and ideas that are, kind of delicious and strange and hard to get our heads around.
Yeah.
Those aren't bubbling up in a vacuum. They're also kind of taking place aside some really sometimes quite dramatic shifts in how we get the work done.
Yeah, I really appreciate that. And it's something that we at Nova, I think, over the last few decades have also started to appreciate, moving away from this sort of lone genius model for how science is advanced, because for the most part, it's actually not. And, often a few people get the credit. The Nobel Prize goes to just, a couple names, right? But it's the way new ideas get created is through interaction.
It is, and what are the conditions to allow those interactions that accentuate some that might put a strain on
Right.
others? And that's sometimes beyond the immediate control, or sometimes even the immediate recognition of the folks that we otherwise, I think you're right, tended to focus on maybe a bit too narrowly. Yeah.
So let's pause on the history for a second. I want to come back
Yep.
to it, but let's do a dive into quantum entanglement.
Terrific. Great.
This phenomenon is hard to understand,
Yeah.
but you probably more than most people have experience trying to explain it. So what's your, I don't know, what's your 3 minute explanation?
Yeah, it's wonderful, I think, and also it is still kind of beguiling. It's not straightforward, and yet as I think you're already setting us up, we have better evidence now than ever before. It really seems to be how our world works, and so it's worth 3 minutes, maybe even four, to try to get our heads around it. So the idea really is that that we often make a lot of good progress, enormous progress over centuries and centuries, in fact, trying to understand the properties of one, say, object, one hunk of matter, and how that hunk of matter might interact with another hunk of matter, but each carrying their own properties with them. And property sounds very abstract. That means if we're talking about little particles, what is its value of its spin along the x direction, let's say? That's a fundamental property of many types of quantum objects, kind of intrinsic angular momentum. We can measure it extremely accurately in laboratories now. It's not a hard notion, even for undergrads to be able to interact with. And so one way we try to describe things like little bits of matter is with their spin along a certain direction in space. Is spinning up or down with respect to, say, the x direction. And so we might think that if we have two particles, we could just attribute a spin to each particle separately and then ask about, the combination of their effects. And that's exactly where things start to break down. That what Bell tests and in this area of entanglement seem to really accentuate is that the value that we measure of, say, the spin of one particle over here is going to be bound up in ways that people found and still find very hard to really wrestle with. What we measure here seems to depend on what happened over there. And the over there could be across a crowded laboratory space, a couple, feet or meters apart. In principle, according to quantum theory, it could be across the galaxy. And that's where it starts hitting up very hard with other things that we take for granted, like local causes yield only local effects. If I hit something here, something shouldn't change there instantaneously. It should take time for some physical process of information or force to move through space over time. And it's that conjunction of ideas that entanglement really forces us to question. Let me unpack that a little further. If I were to to prepare these particles, send them off in opposite directions, and then perform a measurement over here on particle A, I say, oh, I see its spin is spin up along the x direction. Just having performed that measurement is now going to change the measurement outcome for what a colleague is going to find arbitrarily far away. Now, what I can't do is use that to send information. We can't communicate with entanglement, although very smart people have tried for a long time to find a way to do that. What it does is it changes the statistics, the correlations between the measurements that we measure. And so if I only am sitting at one box and I see a stream of particles come at me and I measure the spin up, spin down, spin up, spin up, spin up, spin down, it seems to be a completely random set of basically +1s and -1s. As far as I can tell, there's no information conveyed when I look only at one box that I have access to. What's really remarkable is that when my colleague, who might have been on Alpha Centauri, takes a jet back and we compare our notes, only when we see the complete set of that experiment. What questions did I ask? What measurements did I perform round by round over here? What measurements did my colleague perform on her particle over there, time and time and time and time again? That we see when we each asked certain questions in common, we got related answers. When we asked different questions, those answers also lined up in a spooky way. So the particles are behaving as if they somehow shared joint properties, even though we only saw random noise at one box at a time. So random outcomes at each box, it means I can't send a message to her saying, oh, go, change your stock portfolio, because the correlations only come from seeing the combination of measurements performed and outcomes received. Mm-hmm. Nonetheless, when we get all the logbooks together, we find that the particles are behaving in a correlated way that far exceeds whatever could have happened by chance if each of them had definite properties on their own. If I just try to say each particle had a value of spin before I chose to measure it, I literally get the wrong answer. My friend and I together get the wrong answers. And so by attributing sort of fixed properties to a particle that are revealed by my measurement, by just making that assumption, even saying I don't know what it is, I just assume there's a value that gets revealed, I get different answers for the combined experiment when I bring all the logbooks together than what quantum theory predicts. That might still not be as clarifying as we'd like.
Well, but yeah. So I want to get back to the history because it's essentially, and I see why hippies, New Age movement, Eastern mysticism could see something appealing here.
Right.
Basically, physics seems to be telling us that there is some sort of way that particles are communicating instantaneously, which has a lot of parallels.
Sorry, Ken. I'd be careful with the word communicating, because one thing that came out actually of this group's work was something we now call the no signaling or no communication theorem. So, so it's not like, put it this way, we can guard against the following. We've done this with real experiments now for generations and decades now. If it were communication, then we might expect communication to have to involve, say, sending a signal, even one bit, a 0 or a 1, from this side to that side. And as far as we know, communication has a speed limit, the speed of light, given relativity. And so we're able to do these experiments, experimenting far enough apart from each other, the two boxes, two detectors. There's not time for a single light beam, a single status update on Facebook to get from that device to that device. So they're not communicating. And then lay on top of that, we have no useful information if we only have one box. So we can't receive a signal from the other side and know what it is.
So what is the verb? What are they?
Yeah, it's dissatisfying. I tend to use the word correlated, but because correlation implies you need the whole set to then find these patterns. You need both logs, right? As opposed to like I just got a message in my ear.
Yeah, or behaving as one system almost.
Their behavior is correlated. That's exactly right. So the behaviors are what we measure will show patterns, but we can only suss out those patterns frustratingly and yet bizarrely when we bring the two sets of kind of logbooks together. And that wasn't clear. I should say, even clarifying that was part of what the work of this group that we began talking about really did. One of the members of that group, who was an enthusiastic participant in their discussions, Philippe Eberhard, who was a staff scientist at the Lawrence Berkeley National Laboratory and would meet with them often. He actually was responding to these really joyful, very clever thought experiments that other members of the group were coming up with, exactly to try to send messages. They wanted to have a kind of faster than light telegram. And Philippe Eberhard published one of the first ever demonstrations that even according to quantum theory, that shouldn't work, that won't work, because you need to bring both logbooks together. So we know that. I can say that with a straight face, like, oh, well, there's a no signaling theorem. because of the work of groups like this fundamental physics group, because it was not straightforward. Actually, John Bell himself ended his classic 1964 paper worried that maybe this did leave the door open to fast and light communication because it was so difficult to suss out. So I don't mean to make it sound like it was so straightforward. Over the work, over in that case about a decade, and in the decades ever since then, people clarifying that it's not exactly communication, but there's something certainly spooky or unexpected that still happens.
Mm. So we left the story, the history at John Bell has sort
Yeah.
of envisioned a hypothetical way that this could be experimentally tested. Where does the fundamental physics group come in? What happens next that actually changes the field?
Right. So one of the people who discovered John Bell's article, which otherwise, as I said, was really being ignored, largely ignored in the literature, was at the time a PhD student named John Clauser. Clauser was at the time at Columbia University in New York in the late 60s and early 70s. And he basically found Bell's article by accident. He was in the university library and he found a funny looking journal. Bell published his article not in one of the mainstream journals for all kinds of reasons we can talk about. And basically, as a kind of study break from his main dissertation project, young John Clauser found this weird looking journal on the shelf, and he kind of took it off the shelf, and in great serendipity, kind of semi-randomly, it fell open to where he flipping through found this strange sounding article by John Bell. The title of Bell's article mentioned.
Was it serendipity or was it quantum entanglement?
Right, we'll never know. Well, that's right. I can't rule out either, but it was certainly not. But he didn't go looking for it. I'll put it that way. It's not that Clauser had already heard about the article because few people heard about it.
Mm-hmm.
So by whatever wonderful spooky actions, Clauser found John Bell's article and got very excited. This looked like the kinds of big, how does the world work kinds of questions that had attracted young John Clauser to study physics in the first place. So as Clauser recalls, he rushes back to his dissertation advisor. Look at this amazing thing. We could do these experiments. John Bell was a theoretical physicist. Clauser was a budding experimental physicist. So Bell had identified a type of experiment to perform, but he wasn't prepared to do it himself. Clauser, we could do that. And his advisor said, that looks like, kind of philosophy or not what we should be doing. Do this straightforward project on very, very important topic, but do this other work. And don't bother me with these philosophical trifles, at least as Clauser remembered. It really just a strong brush up. So nonetheless, the topic kind of got under Clauser's skin. He wrote letters to John Bell, asking if other experimentalists had taken it on. Bell was delighted to hear from anyone, let alone an actual experimentalist. Said, no one's done it. Maybe you could do it. That would be amazing. And so they have a little kind of pen pal correspondence. And then slowly, again, through kind of fun accidents, John Clauser is put in touch with other young folks, the few exceptions, who also had kind of found John Bell's article. There was a group in the Boston area and a few others. So John Clauser then completes his dissertation, gets a postdoc at Lawrence Berkeley Laboratory. So to do his kind of to continue his mainstream research. Well, he gets there just as the laboratory, like most of physics, is going through a huge downturn in fortunes. There's lots and lots of kind of, spare time because the funding has been cut way, way back. So he asked permission of his new postdoctoral supervisor, to spend kind of a little portion of his time on this kind of pet project. Could one design a kind of Bell test and really do it? And to his credit, his advisor, Charles Towne, said, sure, you can spend some time on that because, we're not at capacity. And Charles Townes went further and enabled a new PhD student at the time, to start working with John Clauser. And so the two of them were able to work on these first ever, Bell tests. Clauser recalled that he basically got good at dumpster diving. Like there was not like he got grants from, the federal government to do this thing. It was like, what could he scrap for spare parts? And there are photographs that I love of him actually literally duct taping equipment together in this kind of leftover space of the lab. But nonetheless, together, Stuart Friedman, the grad student, and John Clauser were able to do the first ever Bell test. And they found, against what Clauser had hoped for, exactly the correlations that quantum mechanics predicts. I should say both John Bell and John Clauser hoped this would be a way to show that Einstein was right and that quantum theory wasn't really true after all, wasn't as true as correct as could be. That there was something maybe wrong, and then entanglement tests would be a way to reveal that quantum theory is not the last word. And instead, ironically, Clauser and his colleague, younger colleague, Stuart Friedman, actually found beautiful, beautiful, pristine results. Uh,
Everybody wanted to be on Team Einstein. Strong
everyone,
team.
not everyone, but some of these other theories
These
iconically.
guys, yeah.
Yeah. And so to turn that story forward, so Clauser basically shared the Nobel Prize in 2022 for an experiment that he hoped would give opposite results. Maybe we all make such mistakes in the lab. It's pretty great. So that's an example of how the topic began getting local attention. Now, Clauser doing this in Berkeley. He
I
befriended
just
a
want to
bunch of
emphasize
other
that
folks.
that was a Nobel Prize winning experiment.
It turned out to be, with the passage of, in this his case, exactly 50 years. So if you are willing to wait, it was not seen. And in fact, again, not only were people still not paying much attention to John Bell's article, people didn't pay much attention at the time to the Friedman-Clauser experiment. It was published in our most prestigious journal, unlike John Bell's article. And yet it was, again, roundly ignored. You can tell that by citation analysis. There's correspondence from the time that John Clauser himself shared with me and other historian colleagues. This was still kind of dismissed by most kind of, mainstream physicists. In fact, John Clauser never got the kind of position in physics he had hoped for. He never got a university professorship. And some of the letters around his early applications make it clear is because they thought he was working on a kind of unimportant, merely philosophical, kind of strange topic, which 50 years later, earned a share of the Nobel Prize. So that seems hopefully that's humbling for some of us department heads in the world today. Anyway, the point is Clauser really had caught the bug. He now was able to do this remarkable experiment that was not getting a lot of attention. One place it did get attention was his own backyard in Berkeley, when he began meeting up with this fundamental physics group. He was a kind of charter member with about 8 or 10 of other kind of new friends, who almost all of whom were actually coming from theoretical physics. They were intrigued by quantum entanglement and Bell's article, and now they had one of the world experts at their disposal, meaning John Clauser. And together they met, every Friday for years to kind of wrestle with this. Some of them thought this might lead to things like faster than light communication. And some of them thought even further, maybe this would lead to things like an explanation for mind reading. Maybe the communication is between, entangled particles, one of which is in my mind and one of which is in your mind. And so some of them took this into even more, let's say, new agey kinds of directions. They were immersed in a kind of hotbed of new age enthusiasm in the Bay Area. Clauser, I think, to his credit, had a kind of open mind about that. He wasn't sort of convinced about new age stuff, but he also said, "What do we know?" more than once. And he would participate every week, and they would go and have study sessions at other places in the Bay Area, like the Esalen Institute, and Clauser would go time and time again. And he would say, he, as far as I can tell, was, let's say, curious, but not dogmatic in either direction. Some of his discussion mates became much more convinced, and then maybe unconvinced and convinced again. There were kind of strong attitudes and strong passions. The point is, the group didn't feel bound by what counted like to be a straightforward question. They said, if most of us aren't going to get the kinds of careers that we wanted anyway, and these questions seem worth pursuing and curious, they would kind of let their curiosity drive them. And they were combined that with this really grounded disciplined study of they could push the equations around. Some of them could do world-class experiments. So it's that combination that really grabbed me, of a kind of open-minded curiosity combined with the discipline to see it through. And so they weren't just like musing. They weren't just having the late night dormitory room chats. They were open to that. And they were doing their homework, right? And they were trying to say, well, if we take this seriously, here's what my calculations suggest. I could imagine a variation on that experiment. They were trying to do both. And that I found really exciting.
So I hear that these experiments really helped kind of prove that that the universe is spooky, that these phenomena seem to be real. But did that have a direct correlation to the applications? Because it sounds like there were applied physicists already kind of working on applications that relied on the underlying physics. Or did this work also help advance both sides of the equation?
I think it's that it really had a knock-on effect for both sides. I mean, there weren't a lot of people at the time, in fact, none that I can think of, frankly, who were trying to exploit quantum entanglement for new devices at that time. The topic was really just not of much interest either way. And so part of what happened, and partly why I got excited to write the book, was that you start seeing this early group of the kind of eccentrics, and then with their correspondence networks. You could see a small number of other physicists, some of whom were had closer ties to the mainstream and had their own range of curiosities and interests. There's a kind of dispersed community that begins to talk together. Um, some of whom start doing follow-up, very brilliant follow-on experiments beyond the original one that John Clauser and Stuart Friedman had done. And that includes people like Alain Aspect, who then shared the Nobel Prize in 2022. A little later, it involved people like Anton Zeilinger. So there are people and others who begin doing more experiments, kind of riffing on the pattern, but trying to do even more clever versions of the Friedman-Clauser experiment. There are theorists who begin trying to really sit with these challenges from the Berkeley group. Why can't we use quantum entanglement to send messages faster than light if we can't? Does that help us understand other features of quantum theory? And new ideas came out from that. Something called the no cloning theorem was one as a direct response to these kind of clever provocations. So you see this unfolding again over kind of the next decade, from the mid-70s into the mid-80s. And that's when you start seeing now a kind of critical mass in a few pockets, still not on the mainstream in most textbooks, but enough people now beyond just this eccentric Berkeley group who begin wondering, maybe if this really is true of the world, could we put it to work? Does it become a resource and not just a curiosity? And so you start seeing an effort to do things like quantum encryption, which is happening. The first theoretical protocol is being formulated in the mid-1980s, exactly downstream from a decade, 10 years worth of really trying to wrestle with both the first Bell tests and these really clever ideas about the relationship between quantum entanglement, communication, and relativity. And so quantum encryption, becomes really one of the first kind of efforts to apply entanglement in a new kind of device. And that's actually going, yeah, go ahead.
Can you explain that a bit? How does it use entanglement in a device?
Yeah, so the core idea behind encryption is again to say that these entangled particles share features together. And so if someone wanted to kind of eavesdrop on a signal, typically for typical signals, we have one source beaming out, say, radio beacons. And if someone wants to kind of intercept that radio beacon, they can get a sneak preview, right? Because the radio beacon is sort of basically classical system. And so what you do here won't show up over there. If your beacon instead are quantum particles in the special entangled state, then their behavior is correlated. And if someone taps into this particle here, that affects the behavior over there, right? So it changes it basically alerts both sides that someone's actually tapped your line. It announces the fact of eavesdropping, which classical signals are much harder to verify that, and actually erases or scrambles the hope for a message anyway. So the eavesdropper doesn't get the message because they've messed up that special kind of delicate quantum state, and they've announced their presence in brief. So that really relies on these really wonderful but strange properties of, say, pairs of entangled particles, which you don't get through kind of classical communication channels. And that was, again, trying to play with this idea of entangled particles, kind of one quantum state that's somehow distributed through space, combining that with, how do we communicate from this side to that side? The kinds of questions that, among others, this Berkeley group had been really putting their finger on and trying to push. Roughly 10 years later, some other clever folks, some of whom had been in touch with that Berkeley group in the early discussions, they turn it around and say, oh, actually, this becomes a way to protect information as opposed to a way to send it somehow by magic. So, and then now that's really a kind of worldwide part of $1 billion worldwide industry now. That's one example.
So quantum encryption is one example. What other applications of quantum entanglement are we seeing now?
So another big one, another big one, there are several. Another big one is actually on quantum computing, which is not quite as far advanced in terms of kind of entering the kind of everyone getting to buy one on Amazon. But quantum computing is an area that's also a subject of enormous effort and enthusiasm and funding and support in universities, in government labs, in private industries, everywhere, in many, many countries. And at the core of many kind of quantum algorithms is again these kind of entangled states. Now we call them Bell states. They're trying to use these special prepared kind of pairs of particles can really kind of take advantage of their connectedness. So instead of having lots of particles, lots of bits calculating kind of in parallel on their own, you actually can get these for certain kinds of tasks. You can exploit the connectedness, and in some loose sense, exploit the fact that that one state is, again, more than the sum of its parts. You're getting kind of more computation out from one entangled system than you would ever get from having two kind of separated or classical bits. There's much more to it, but the point is that a lot of the kind of speed up or the power behind many of the algorithms that are designed to run on quantum computers really comes from exploiting this connectedness, these Bell states. So that's another kind of on the horizon, not quite on the shelf yet today, technology.
So what do you think the future might look like with respect to how quantum technologies might change the world? I mean, we're living right now through what seems to be like an AI revolution. It seems like it's changing a lot. Is there going to be a quantum revolution where just the fabric of the way society works, it changes because of these technologies?
Likely so, but it's going to come in stages. I think most big changes tend to actually. So one is, I think one thing that people would love to be able to do if they can get kind of robust quantum computers to really run on a larger scale would be to start simulating quantum materials. As we've been saying now, quantum mechanics just says that matter behaves just differently than kind of large blocks of matter behave that are otherwise described so well by classical physics. And so our computers to this day, our ordinary computers, are really good at simulating ordinary matter. Even that's hard, but we've gotten really good at it. They get really, really bad very quickly at simulating quantum states of matter because of these kind of exponential kind of connectedness, let's say. And that really just swamps what even our best supercomputers can do today. Quantum computers would, so to speak that native language of quantum theory itself. And so one hope would be to have just an unbelievably improved ability to understand materials at a quantum mechanical level, maybe even design materials. Maybe that gets even a few steps down the road to things like pharmaceuticals. I don't know. But what do we want to do? I mean, if matter is made of quantum objects, can we learn to understand and maybe even manipulate quantum objects, quantum materials in a kind of more thorough grounded first principles way with a ability to simulate those that equals our kind of imagination, let's say. That would be one great thing.
So like a quantum computer could run a fusion reactor because it's a quantum process or something like that.
Maybe so. Or would it help us understand, again, some maybe bioactive molecules better than we are able to now, things like that.
Would there be some sort of spooky kind of black box aspect to how quantum computers actually do their computing the same way, AI is kind of a black box right now?
I think that's probably right. And so that's right. So people spend a lot of time trying to understand quantum algorithms. But as these go up to scale, I think one would likely start to find things like we find, huge machine learning algorithms or behind things like generative AI that really exceed a kind of human interpretability or human explainability. I would expect the same thing to happen as these quantum algorithms, again, grow in their own complexity.
What do you think? What's your expectation for the timeline when we might actually see this in our lives?
It's tricky. For quantum encryption, I think it's already in some sense here. It's in pretty advanced beta testing. I have friends and colleagues who have done this as kind of demonstrations, but not just in pristine laboratory conditions, real world demos with kilometers and kilometers of fiber optic cables strung through cities, not just in kind of laboratory or university buildings, and showing that encryption systems really do work as designed, and they can be deployed not quite at scale, but beyond only kind of controlled conditions. So I think encryption is frankly further along in getting closer to something that could really be of commercial and governmental use, for good or ill. I mean, I'm not sure that's a good thing, frankly, but nonetheless, I think it's much closer. Quantum computing, I think one of the big limits, maybe the biggest limit so far, is not designing really cool algorithms, not designing the code we love to run on these things, but getting enough of these very kind of delicate quantum states, these so-called qubits or quantum bits, to maintain their special quantum state, because basically heat and noise are the enemies of quantum coherence. So to really, put it another way, we work really hard when we do these experiments to reveal quantum entanglement, like modern day Bell tests. We have to shield our quantum particles against all kinds of disturbances, against noise. And so imagine trying to do that with lots and lots and lots of these quantum
Mhm.
particles, these quantum entangled particles, because many, many kinds of effects of the environment will tend to wash out that special quantum state and therefore wash out that kind of quantumness that you want to exploit.
So forgive me if this is a little bit of a 101 question,
Yeah.
but when does something become quantum? I mean, obviously
Well,
we don't see our stuff in our world regularly entangled. Is there a reason for that, or is there a line at which
so
physicists say this is quantum, this is not?
it's the opposite of a one-on-one question, Kate. That's still at the cutting edge, frankly. It's
Good.
it's a deep question, um, and so I'll give you a shallow answer. But I'll just say there is no single kind of dividing line. It depends on, the system and the means with which you're interacting with it. Nonetheless, one of the great kind of races that's on today, again involving some of my very dear colleagues and friends, is see exactly how large, how many moving parts a system they could make that still shows the unmistakable quantumness, and when does the classical description kind of take over and become thoroughly adequate? And that's a moving target. We know that if we want to describe a single atom at a time, we're not going to be able to do it with Newton's physics. We know, just as you said, we want to describe a huge collection of atoms, then we do really well with classical physics. And where's that line? Is it, 10 atoms? Is it 100,000 atoms? Is it 10 million atoms? And that I think really becomes kind of context specific. But part of the kind of virtuosity is to be able to demonstrate robust quantum behaviors for systems that have lots and lots of quantum moving parts, but not so many that it's kind of tipped over and the quantumness kind of washes out. So again, that's a bit of a vague answer, but I'll just say it's a live issue. And part of what even for those demonstrations, part of what's so tricky is that, as I say, kind of an impacts of the environment, which can take many forms, tend to wash out the special quantumness of one system or of these complicated many part systems. So that's what creates one of the main drags on quantum computers is how many of these so-called qubits of these specially prepared quantum states can you keep in their quantumness, in their quantum state,
Mm,
before that kind of washes out and their special bell-like behavior, quantum entanglement behavior, no longer becomes usable because it's been kind of diluted, because the entanglement's been kind of spread out among
mm.
so many partners that it no longer has that specialness between, say, these two members of an entangled pair. So again, that's a bit of a imprecise answer, but I think the biggest challenge right now is maintaining large numbers of the stuff on which you could run quantum algorithms.
So speaking of things losing their quantum state or changing
Yeah.
them, there's another aspect of quantum entanglement that is strange,
Mhm.
which is about how the observer can affect the system,
Mhm.
which is troubling in some ways. Can you explain a little bit about that?
Yeah, that's another one that sort of won't go away. And I should also say it doesn't command a single answer even among experts in the field. It's an area people still really get rightly troubled by, and many people have their own favorite answers, but they're not, it's not the same answer. So again, if we take the equations of quantum theory at face value, it certainly looks as if, and many people, smart people, including Nobel laureates, have described quantum theory as somehow relying on the observer to produce a certain outcome, that we choose what measurement to perform, and therefore the outcomes of measurements are sort of unavoidably dependent on our choice, at least of what to do, or how we chose to intervene, what setting we set on our measuring device, and therefore what answer we got. Especially if we combine that with what we talked about some time ago about entanglement, that we no longer can describe these quantum measurements as just having fixed properties that our measurements happen to reveal, right? It's that really puts the tension on what's often called the measurement problem, that we chose what measurement to perform, and that revealed a definite answer. It's not that we get a fuzzy or squished out answer. We get a real
Mhm.
answer. We just might not have gotten the same answer, the next time around. So what role did we play in kind of manifesting or bringing forth a particular measurement outcome because we chose for a measurement? So some people take that and say, one person in particular, Eugene Wigner, thought that was just really unavoidable, and that somehow human consciousness had a role to play in quantum theory. Wigner, I should say, won the Nobel Prize in Physics. He was not a dummy. His ideas commanded lots of attention, including from this Berkeley group. Some of them were enamored of that. Is there a reason why human consciousness should be somehow written into the equations of quantum theory? They were intrigued. I don't think they quite succeeded at that, but they were intrigued by that question. These days, that line of thinking is much less popular, let's say, among experts in quantum theory. It's not that it's been sort of disproven necessarily, but other folks have found other roads. One that's popular, and it's not one that I particularly endorse, but it gets a lot of people excited, is something called the many worlds interpretation, which basically says that that all the answers are chosen. It's just that the universe kind of splits in some sense every time a measurement is performed, so that our human consciousness, me here, also winds up splitting. And along this path, or in this, this track, there's a version, it's all self-consistent. There's a version of me that found the electron spin up. But at that moment, there was a split, and there's a version of me in a track with which I had no longer have any contact, that in my consciousness found the outcome to spin down, and so on and so on and so on. You can imagine this infinite proliferation. I find that pretty heady and pretty dizzying. I have very dear friends who think that's the most straightforward way to understand what quantum theory is telling us. So it's not that my consciousness is acting in the world, but in some sense, my consciousness is bound up because it's also made of quantum particles, and all this entire quantum assembly is always doing self-consistent things, but I can no longer track. I can no longer send or receive messages from these kind of now parallel tracks that have somehow forked off. Now, that's a great way to make some pretty cool science fiction. Some friends of mine think it's a great way to describe the natural world. Obviously, that hasn't commanded, universal acclaim either. There's all kinds of things which get at exactly what you put your finger on, Caitlin. What is the role of, let's say, the observer in our interactions with the quantum world?
And I can see how the fundamental physics group would see this as really compelling, because physics seems to suggest that we have a role we have agency in creating the universe that comes to be.
For some of them, I mean, again, that was at least an enormously consequential question. And a lot of them, to their credit, didn't say, I found the answer, I'm right. They said, that's a question worth sitting with, right? And so I think it was their openness to the questions that really I just came to admire. Not all their answers. Some of their answers I thought were actually, frankly, pretty silly. Some of them came to consider those answers silly too over time. Not all of it, not all. And again, it was a rich variety. But to be open to ask questions that otherwise seemed strange or silly. I mean, a lot of questions seem strange or silly at first, and some of those, not all, but some of those questions, when we bring our kind of disciplined thinking to them, can really surprise us. And so that's what I found so, frankly, endearing about the group.
So what happened to this group? Did it disband? Did they all just become popular physics? What happened?
Yeah, it was kind of accidents of history that by which they found each other in the early and mid 70s. And then by the late 70s, early 80s, they began to kind of, go their own ways. So some of them stayed in the Bay Area. Some of them moved on geographically. Some of them became kind of very clever consultants. We might call them kind of entrepreneurs these days. All kinds of tasks, some of which failed, some of which, succeeded on the margins. One of them won the Nobel Prize, right? And so it really it's a huge range of rags to riches, to for some of them rags again, or to others, a kind of lasting place in our understanding of how we've come to where we are today. So, and many of them, I should say, many of them are still alive. One or two have indeed passed away only recently. They were doing this when they were in their 20s and 30s 50 years ago, and so many of them are around. They were around when I was working on the book, and they were very generous with their time when I had questions, and they would always get back to me right away, and I had a chance to meet and talk with them. And I still hear from many of them to this day. So, I think all of them have kept a sense of the wonder. I think that's fair to say. Some of them have pursued even more, let's say, heady topics that are on the fringe or outside the mainstream. About, say, could we understand UFOs? Are there ways to understand relativity in non-canonical or non-unusual ways that might lead to strange effects? Again, I'm not endorsing those claims, but at least you can see them puzzling through them. And others, like I say, have now reached the very pinnacle of success in our field, like John Clauser. So it's a whole range.
And their legacy is that physics has continued to pursue these these questions. And I understand I want to pivot a little bit to talk a little bit about your work. So I know you were involved, at least at least in some respect, with
Yeah,
a quantum Bell test, a cosmic Bell test. Tell us
right.
about that.
Yeah, I was. So it was really quite it was one of the adventures of my life. It wasn't just a highlight of my career. It was even more special than that. But I'd written the book that we've been talking about, and then after it came out, some of the young physicists with whom I work had read the book kind of for fun. It had a strange title, and they were curious, so they read the book for fun. And then we began talking about, well, could we imagine redoing or doing a new generation of Bell tests, using what we all have learned in the interim over the last several decades, not just about quantum theory, but about the structure of the universe. So my younger colleagues and I were coming at this from astrophysics and cosmology, not first and foremost from quantum physics per se. And we've learned a lot about the Big Bang, about the kind of course of the universe over the last almost 14 billion years, about the kind of causal structure, which parts of the universe could have interacted with other parts over time. And so working with Andy Friedman and Jason Colicchio, they were at the time very young postdocs, we began wondering whether we could visit one of the most stubborn kind of loopholes in these generations of Bell tests, which was often called the freedom of choice loophole, or the free will loophole, which is a bit more sensationalistic. But the idea was, in any Bell test, we have these two devices, and physicists locally at each one have to choose what measurement to perform in real time before a member of the pair arrives. And so we have to do something like flip a coin. And so the question that was identified in the mid-70s by people like John Clauser, and talked about it and debated it with people like John Bell, but was never really tackled in new experiments, was, how do we know that we're using a fair coin? How do we know there was no hidden coordination or statistical correlation between the choices of what measurements to perform here and there? Was there something in the shared past that could have either tipped off the far side of the order in which measurements will be performed, or maybe even nudged them both? Relativity says that things that are far apart can interact. It just takes some time. Well, we've had 14 billion years of time, right, since the Big Bang. So the question was, could there have been something in the shared past, some subtle effect that had been overlooked, that could have kind of led to a correlation in the order in which questions were asked, even though those devices are so far apart from each other today? And so we decided to turn to the heavens, to turn the universe into a pair of random number generators, not flip a coin, in our local laboratory, but turn to random processes far away and long ago on opposite sides of the sky. And that's what put the cosmic in Cosmic Bell. So we proposed this. We wrote a paper saying this is feasible. There's light from very distant quasars, very bright, very early galaxies on opposite sides of the sky that lit up so early after the Big Bang that they had no chance to trade light signals with each other. The light would be traveling through most of cosmic history toward the Earth. Could we use those as our decision makers? When we get this light on our mountaintop, this moment, that light was emitted very early in cosmic history. Depending on the properties of that light we receive, that will tell us what measurement to perform here on our earthbound entangled particle, and so on over there. So we want those quasar signals to be as unentangled as possible, as uncorrelated as possible. And the universe is a big old place. So it turns out one can search for really distant sources of light that were coming from opposite, kind of separated parts of the sky, and then do an earthbound test that way. So we pitched this idea. Go ahead, yeah.
So you're using the entire universe in your experiment?
96% of it. Yes, we use an enormous
Is this
fraction.
the largest experiment ever done?
Well, it depends on how we characterize it. But it certainly was among the biggest. It was trying to push quantum theory and relativity out of their shared comfort zones. Let's put it that way. Right, so it's really trying to ask questions about fundamental quantum theory with some real inputs to the experiment that span cosmic scales. That's certainly right. So I don't know if it was the biggest ever, but it was certainly trying to do that in an unusual way. So as us theorists, we said this could work. We pitched it to Anton Zeilinger, and he lit up immediately, and he got very enthusiastic. He and his group had thought similar questions, as we then found out. So we put a team together, and we finally got some generous support from the National Science Foundation. And so we built this international collaboration. We really did this. We did a pilot test in Anton's home city of Vienna. And based on how well that one turned out, we did a big test on the island of La Palma in the Canary Islands with huge 4-meter telescopes. It was just a joy. And that was captured partly in this NOVA film, Einstein's Quantum Riddle. The filmmakers were there. They got some, I think, breathtaking footage of what it's like to work on a mountaintop observatory, which is just jaw-droppingly beautiful. They captured us in moments of real uncertainty. We got bad weather several nights. We were iced out, chased down the mountaintop midway down because for the first few nights there were ice storms, and if we didn't leave, we'd have to sleep in the telescope dome, basically. So it was really, wasn't so straightforward. And the filmmaker was there to catch, kind of the highs and the lows both, which I'm really grateful for because it's, I have my fond memories, but I can go back and watch the footage too and say, wow, this is a team of 20 people working literally around the clock, and it was just a huge adventure.
Thank you for doing the promo for me. You did my job.
So,
if you want to check that out, that's on our website, Nova. Maybe we can drop the link in the chat as well. But yes, we did follow that experiment a few years ago.
That's right.
So what mysteries of the universe are you trying to solve now?
Well, there are a couple left. There's a few mysteries left. We're not going out of work anytime soon. One of the ones that I find most delightful and challenging, really hard, pivots a little bit away from quantum entanglement, but it still gets to like, what's the world made of? I love those kinds of questions. And one puzzle that's been with us for at least 50 years and has trails even earlier, around the same time that the fundamental physics group was really forming and beginning to wonder about quantum entanglement, people in other areas of the field began to realize that our universe is chock full of this mysterious stuff that we now call dark matter. We don't know what it is, and yet it seems to be everywhere, and it seems to really have set our universe on its course. In fact, we need now to take into account an enormous amount of dark matter if we're to understand how the universe has evolved, and in some sense, even why we're here. Without dark matter, it's not clear that galaxies could have formed, at least not at the same rate or the same type that we have today. Maybe our own galaxy couldn't have formed if there was no Milky Way galaxy. There probably wouldn't be a sun or an Earth here, for us to live on and ask questions about the universe.
I have some dark matter here.
Yes.
From physics at MIT.
Peter Fisher has a bunch on his shelf too. I recognize the box. And so if
there's some dark matter in here, a very small amount.
Yes, there's approximately one per that volume. That box is great to show us just how thinly spread out it is in our local setting. There'll be about roughly one proton's worth, one hydrogen nucleus worth per box that size, per cubic centimeter. Anyway, so maybe it's a few more than that. But anyway, it's pretty thin on the ground. But when you add up how many cubic centimeters there are in the entire universe, this stuff dominates. It's much more, about 5 times more dark matter per unit mass than all the ordinary matter that we know about. The entire periodic table that humanity spent a couple hundred years piecing together and testing. Throw in all the fancy stuff we learned about from the Large Hadron Collider and experiments before that, the Higgs boson, neutrinos, throw in all you want, with lots of great nova special in those too. Those make up roughly 20% by mass of the matter that seems to fill our universe. So we have a big, big challenge. What is dark matter? Okay, well, one of my favorite hypotheses now is to say, what if it's not some exotic new particle that no one's been able to find after 50 years of careful testing? What if instead dark matter consists of ordinary matter, the stuff that we do know a lot about, that's locked up in unusual gravitational states known as black holes? Again, lots of great nova stuff on black holes. Mm-hmm. But what if these are not just ordinary black holes that we now know a lot about? What if these are special black holes that formed right after the Big Bang? They're called primordial or early universe black holes. They formed by kind of doing an end run, by cutting out the typical life course by which ordinary black holes are made. These would have been made long before there were atoms, let alone stars that collapsed to make astrophysical or stellar black holes. And Stephen Hawking, among others, hypothesized about these 50 years ago in the mid-1970s. The idea was, like quantum entanglement, kind of on the fringe for a long time, even though elite physicists, like in this case, Stephen Hawking, had put it forward. It was seen as a curiosity at best, or a weird idea, or not worth pursuing. And really, over the last roughly 10 years, this hypothesis has come roaring back into interest, partly because these other much better motivated, or seemingly better motivated hypotheses, like, oh, it's just some new particle, keep coming up empty. It doesn't mean the answer is primordial black holes, but it gets really intriguing because now we know black holes are real. That wasn't so clear at all in 1974. We can find other kinds of black holes now all the time with amazing astrophysical instruments. We've learned a lot theoretically. Anyway, we know a lot. We know a lot about the early universe, what could have led to the formation of a population of these black holes early on. We just know more of these puzzle pieces, and a lot of them feel much more solid than they did when this was merely hypothetical 50 years ago.
So are you saying there could be a primordial tiny black hole in my office?
Yes, yes. At the very now, it's not very
They
likely.
are among us.
They might be among us. In
Might
fact,
be.
with very dear colleagues, I've been doing some work on that exact question, as have others. If all of dark matter consists of these tiny black holes, they would have to have a mass that was around the size of an asteroid. They'd be like big space rocks in mass, but they're black holes, which means they've condensed, they've shrunk that mass down to an impossibly small spatial size. They're so densely packed. You take the mass of an asteroid, a big space rock, and you shrink it down to the size of an atom or smaller. So it's a really, really amazing exotic object. It has very interesting and strange properties. So now, if that's all of dark matter, then you only need to sprinkle a couple of those around the solar system to make up for all the dark matter by mass that we know has to be there, because each one is much more massive than, say, a typical particle. So the number per volume goes down. It's much less likely to have one in your office, Caitlin. Very unlikely.
I don't think
But
there's something the mass of an
but
asteroid in my office.
probably you'd know that
I
if it
know.
were that close, you'd be tugging on, you'd feel it to be. But instead, there should be about one, at least one or two within a sphere the size of, say, Jupiter's orbit. And it could be anywhere in that sphere, right? And it could be zipping around at high speeds.
But you
So it's
could
not
presumably detect that astronomically then.
exactly right. And so we have this really fun paper that's coming out soon, actually, coming out in one of the physics journals, saying if that's really the case, then there should be observable signals of visible objects that we track with great care, like the position of the planet Mars, right? Thanks to 20 plus years of high precision telemetry to Mars orbiters and Mars rovers, astronomers know the Earth-Mars distance to an incredible accuracy, to 10 centimeters. Amazing. We know the distance between Earth and Mars to 1/10 of a meter, thanks to all these very cool, basically space program projects. That's amazing. So now let's say some little tiny black hole goes zipping through the solar system, doesn't hit anything, right? It's mostly passing through empty space, but it has enough mass and is going so fast, it sets Mars rocking just a little bit. We're not talking about a Hollywood blockbuster. It's not Armageddon. It's a tiny little shift, a kind of rocking motion that would result in, say, the planet Mars. But we monitor Mars so well that rocking motion should indeed be observable over not such a long time period. It should have a different kind of rocking motion than if other kinds of, say, space debris flew past. So we have reason to think it could be separated from kind of other more mundane explanations for these kind of little wiggles. So this is the kind of thing we can now try to do. Other colleagues wrote some really interesting papers saying, what about the GPS satellite network? We know the positions of 30 satellites to about centimeter accuracy, and we've known that for decades. So we have kind of historical legacy data as well as going forward. They're tracked so carefully because we need them for our navigation. Again, if some get a little wobble, not a huge effect, would it show up in that kind of system as well? So there's hope to think maybe we could test this bizarre sounding hypothesis. What if all of dark matter is locked up in these tiny, tiny microscopic black holes formed by the Big Bang? It sounds like ridiculous. We might know. We might be able to tell over the coming decade or two. And I find that great.
Fascinating. So you think in the next couple of decades we'll have the observations to sort of verify or disprove this?
I think that's right. I mean, I think if no such wobbles show up, then that becomes a pretty tight constraint. If a couple wobbles do show up, then we'll have to play the usual game of, well, was it really a black hole? Was a different mundane explanation we overlooked? It'll be hard. But if you find nothing that crosses the threshold, then it's going to be harder to account for if all of dark matter is black holes. So it really does seem promising as a way to constrain and intriguing as a way to at least get some hints if there really were these wobbles that could be found. And that is on a kind of decade-long time scale, not impossibly far into the future, but we won't know tomorrow, but we might really know something concrete over the coming years.
Fascinating.
Yeah.
Well, we are already well over time. David, where can folks keep up with your work going forward if they want to know the results of your black hole tests and
Well, I'm not on social media, but I am. I have a website, a very old-fashioned website, and I do keep that pretty up to date. And so all our physics papers are available totally for free and open access on the preprint server, even before they come out in the journals. My colleagues and I, really, it's quite common throughout physics to make sure that anyone can see them without, any paywall or restrictions. I'm always updating it there to papers. I write a lot of kind of more accessible essays about those things. I also make sure those are on the website and try to share them that way too. And of course, I love working with you and the team for Nova and other fun things on YouTube. So hopefully that combination will help folks who are curious.
that's great. Yes, you can watch any of the films David appears in on our website or on the PBS app. If you want my top pick for right now, I would go check out Einstein's Quantum Riddle because that delves into and explains further what we just have been talking about in this conversation today. David's also going to appear in Decoding the Universe Quantum coming up this fall. So stay tuned for that. David, thank you so much for joining us. As always, a pleasure to talk to you.
Really, Caitlin, thanks. It was really fun for me, and I hope folks enjoy the chat. Thank you.
Thank you.